let's talk about solubility curves. But first, let's talk about dissolving stuff in water. So NaCl is a salt. In this example, I'm using table salt, but a salt is just going to be an ionic compound. Now, ionic compounds, they have this crystal lattice. Now, if we take a look at water, this is my water right over here. This red thing is my oxygen, and these two white little things are my hydrogens. This is why it's H2O, right? Two hydrogens, and the big one is my oxygen. Now, recall that H2O is polar, all right? Basically, oxygen and hydrogen, they are both sharing electrons, right? This is a covalent compound. However, this sharing of electrons is more in oxygen's favor. It's more in oxygen's favor than hydrogen's favor. So even though they're still sharing electrons, the electrons are going to like to be closer to oxygen than hydrogen. So because oxygen has sort of gained a negative charge, it's not a full negative charge because, well, it's still sharing electrons, but the electrons are a little bit closer to oxygen. Well, oxygen has gained something known as a partial negative charge, right? You gained a partial negative charge, not a full negative charge. Meanwhile, hydrogen, it hasn't lost the electron, but it's sort of like the electron's further away from from hydrogen now, right? The electrons like to be closer to oxygen, so hydrogen is kind of like stripped away a bit of the electrons. If you lose a little bit of a negative charge, you're becoming more positively charged. So these hydrogens have gained a partial positive charge, right? Now, let's put a water molecule next to let's put this water molecule next to my ionic compound and let's see what happens. H2O molecules. All of the oxygens will be facing my Na plus ion because they are attracted to the positive charge of the Na plus ion. Likewise, remember, my hydrogens are partially positive charged. And that means that, well, a positive charge is going to get attracted to a negative charge. So you can imagine that these hydrogens are attracted to this Cl minus anion. So hydrogen and chlorine or chloride ion is going to be attracted to each other, while the oxygen and the sodium ion is going to be attracted to each other. Now, this is just a simple diagram, but you can imagine that there's hella water molecules around my ionic compound. So imagine if there's many, 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 many water molecules around my ionic compound. Well, eventually, the force or this attraction that the ionic compound has with the water molecules is going to be greater than the attractions that the ionic compounds has with essentially itself, right? This Na plus ion attraction with itself, that this Na plus ion is sort of going to get pulled away. It's going to get pulled away from the ionic compound. In this time, the hydrogens are actually facing the chloride ion. And the reason why is because, remember, hydrogen is partial positive charge. It has a partial positive charge. And that means this positive charge is going to get attracted to this negative charge. Okay, so always remember, opposites attract. The partial positive charge gets attracted to my negative charge. Meanwhile, this oxygen is only going to be attracted to, in this case, my Na plus ion in the previous example. It's going to be attracted to the Na plus ion mainly. So this is what's going to happen. Essentially, this chloride anion is going to be sort of ripped away by this hydrogen, right? The attraction to the hydrogens is now stronger than this chloride ion's attraction to the other ions, that it sort of gets ripped away. There's so many water molecules here that it gets ripped away essentially from the rest of its friends. And this is going to just happen, with the other ions. This Na plus ion gets attracted to this oxygen. It's going to be sort of ripped away from this attraction. And now, after everything has been dissolved, or after some of the ions have been dissolved, well, these dissolved ions will form spheres of hydrations. This is what it's called. It's going to form spheres when the ion kind of gets surrounded by the water molecules in a sort of sphere. All right, and the reason why that happens is because, remember, hydrogen, oxygen, they only have partial charges. All right, they only have partial charges. However, ions, they have complete charges. They have a complete sort of formal charge, right? And that means that the water molecules are going to be more strongly attracted to my ions than to each other, meaning that the water molecules want to be around all of these ions more than they want to be around, well, themselves. This time, if I were to kind of draw this diagram, it would look like this. So now, because my Cl minus is a Cl minus charge. Negative charges get attracted to my partial positive hydrogens. So all of these hydrogens are going to attract my Cl minus ion, and yeah, it's going to form this sphere of hydration. Now you can see for table G, this is solubility curves at standard pressure. X-axis is my temperature, y-axis is the solubility. And this is going to be for 100 grams of water. All right, we're keeping the amount of water we have constant because the more water we have, well, as the amount of water we have increases, well, more stuff is able to be dissolved, or the fancy term for it is solubility. So the more water we have, the higher the solubility. All right, solubility is just a measure of how well does a salt dissolve in water. Now, because water is one of the factors that determine solubility, and another factor is going to be temperature. As you can see, as temperature increases, it looks like for a lot of my ionic compounds, my solubility also increases. And this is specifically for solid ionic compounds. You can, of course, see some exceptions, and we'll talk about those. We'll talk about those lines later. But you can see that for solids, as temperature increases, their solubility in water is going to increase. You can see that around 70 degrees Celsius, 150 grams of, in this case, KNO3, right? It points to this line. 150 grams of KNO3 is able to dissolve in water at 70 degrees Celsius, around that temperature. And let's compare this to, let's say, 60 degrees Celsius. And at 60 degrees Celsius, only around 110 grams of my KNO3 is able to be dissolved. So you can see that relationship from this chart. Now, why is that? Well, what is temperature in the first place? Temperature is a measure of average kinetic energy. Okay. So as the temperature increases, well, the kinetic energy is essentially the speed of our water molecules are going to be increasing, right? And if the water molecules are moving faster, that means that more water molecules are essentially going to be able to interact with my ionic compound and be able to sort of rip it away from the other ions, right? Now, another reason why, as you increase the temperature, the solubility for a solid increases. If you guys do not know this, well, you're gonna learn it. Probably gonna learn it later on. But a lot of times when you dissolve a salt, it's gonna be endothermic, meaning that you're gonna absorb heat. You're gonna absorb heat, right? So essentially, what's gonna happen is that when I dissolve my salt in water, that's going to absorb some heat. And if I increase my temperature, that's essentially adding more heat. And more heat means that, well, more of this KNO3, in this case, is going to react. So my reaction is actually going to shift to the right. More of this KNO3 is going to dissolve, and therefore my solubility actually increases, as you can see. So that's another explanation for that. Exceptions I was talking about. And let's take a look at ammonia. So ammonia is actually a gas. And you can see that for gases, as the temperature increases, my solubility actually decreases. So for gases, as temperature increases, my solubility decreases. Okay, that makes sense. I mean, if I have like a soda can, right? Now, you know, soda, it's filled with like that syrup mixture, right? Syrup mixture, that's what makes like the Coke taste sweet. But then to make the soda fizzy, you have carbon dioxide pumped into there. Imagine you're just sipping on Coke on a hot summer day. Now, if it's a really hot day, well, we said how temperature is a measure of average kinetic energy, meaning that the higher the temperature is, the faster these gas particles are going to move. And therefore, if this is like the opening to the can, the gas particles moving so fast, the gas particles are going to be moving so fast that so many of them are actually going to escape out through this little opening, right? So the higher the temperature, well, the more likely that the gas particles actually escape from whatever mixture it is dissolved in, and less of it is actually going to be dissolved in the mixture, right? A lot of it is going to escape. But let's also talk about pressure. So how does pressure, for gases, how does pressure affect solubility? What do you guys think? Well, let's do another experiment. Let's say that we have the same Coca-Cola can, except this time, let's say that we have our syrup mixture, whatever thing, sweet thing down here, and we have our gas here. Now, what's going to happen is I'm going to have like a piston, so like a little like piston, you know, Oh, that is an awful color for this. Let's say that I have a piston and it's going to be like pressed down, like a hydraulic press, right? So what's going to happen if I increase the pressure by moving down this piston, right? Because obviously, the pressure is just when the gas particle, when some of the gas particles, they hit the wall and they exert a force on it, right? And that contributes to the overall pressure. Now, if I kind of move this piston downwards, well, then the gas particles are going to be in a much smaller area than they were before. You can see how now our gas particles are kind of forced to be inside and dissolved in our syrup mixture. So you can see how when I increase the pressure, right, by moving down this piston and allowing the gas particles to be more clumped and hit the walls more, right? Because if you decrease the volume of this container, the gas particles are just going to hit the wall more, causing the pressure to increase, right? When I increase the pressure, you can see that the gas particles are essentially forced to be in a certain area, and they don't really have a choice. They have to kind of be dissolved in this syrup mixture. So my solubility is actually going to increase. Now let's get a little bit more familiar with the terms of solubility. So here we can have something known as a saturated solution. Anything on the lines is considered a saturated solution. For example, let's look at KNO3 once again. If I pick this point on a line, this is saying that, well, if I dissolve around temperature of 65 degrees Celsius, I'm able to dissolve around 120 grams of my salt. Well, in a saturated solution, you've kind of reached the maximum amount of salt that you can dissolve. Okay. So saturated solution, the maximum amount of solute, or in this case my salt, right? The maximum amount of my salt that I can dissolve in my water, and this is a saturated solution. Anything on a line is a saturated solution. Now imagine if I go above the line. Let's say I pick a point up here. So we're still at the same temperature, but this time I'm trying to dissolve more salt than my water can handle, right? This is a little too much salt than my water can handle. So when there's too much salt in your water, this is something known as a supersaturated. So in a saturated solution, you'll typically see that, well, most of the salt has been dissolved, right? That's a saturated solution. And this contains the maximum amount of solute that can be able to dissolve in the water. In this case, solute just means the thing that you're dissolving. So solute just refers to our salt, right? The thing that we are dissolving. Now we have dissolved the maximum amount of salt in my solution, and some of the salt will recrystallize. So this is recrystallize, right? Some of the salt will actually recrystallize and come back into ionic compound. And at the same time, some of the salt will actually be dissolving. So the rate at which some of the salt is turning back into these crystals is the same rate as the rate at which the salt actually dissolves in the water. So this is going to be in like an equilibrium. We call this a dynamic equilibrium. And the way you kind of express this is that, let's say we're starting off with KNO3, right? And this is in the solid phase. And this is going to be in equilibrium, so we show it with these arrows. This tells us that this is like a reversible reaction, meaning that we can go both ways, essentially. And this is going to dissolve into the K plus ion, which is going to be dissolved in water. And this is going to also turn into the NO3 minus anion, which is going to be dissolved in the water. So this is how you would write it out in a chemical reaction. This is going to be at equilibrium. I'm just putting at equilibrium up top in the arrow here to show that this is at equilibrium. But the main thing to know is that the rate at which our KNO3 dissolves into these ions in the solution is the same rate as these ions sort of recrystallizing back into KNO3. Okay, let's just move this down. Now, in a supersaturated solution, we have way too much salt. Our water essentially cannot handle the amount of salt that we have, right? We have dissolved, you can see here, we have dissolved too much salt in my water that my water can actually handle. And what you'll actually see is you'll see a lot of crystals this time, right? And actually the rate at which the salt sort of recrystallizes is now going to be greater than the rate at which the salt dissolves. There's not going to be much dissolving happening because there's a little too much. And this is going to be, supersaturated solutions are going to be like unstable. So like any sort of tiny disturbance, any sort of tiny change lets actually a lot of ions. So any kind of scratch or anything, that's going to allow a lot of ions to sort of gather together quickly, and that actually is going to form a lot of crystals rapidly. All right. So like an experiment you can do at home is like you can start off with like a saturated solution and you just add a little bit more so that it becomes super saturated, and what you'll see is a lot of crystals forming. Okay. Finally, if you look at my graph right over here, what happens if I go under this curve? What happens if I go under this curve? Oh, now you can see that when I go under this curve, now we are dissolving less solute than my solution can handle. Right, so we still have the same solution. This time we're just putting in less salt. So this time in my solution, drop the water. This time we're only putting in a little bit of salt, and all of the salt is going to dissolve. There's actually going to be no crystals. If you just look at the solution from your perspective, it looks like nothing is in the water because all of it is dissolved. So the rate at which everything is dissolving is greater than the rate of which things are recrystallizing because nothing is crystallizing. Everything has been dissolved. Okay. Now, there are a couple ways for you to become super saturated. So one way to become super saturated is, we talked about this before, but you could just add more solute, right? If you dissolve more salt than my solution can handle, that's going to cause things to be super saturated. But another way I can become super saturated is if I decrease the temperature. You can see how if I decrease the temperature, now I have a super saturated solution, right? Normally I should be here for a saturated solution, but now I'm actually up here. So you can see decreasing the temperature and actually adding more solute is actually going to turn your things into the super saturated solution. Okay,